Okay, great. So shall we begin? Yeah, Ganesh, can you start the recording?
Yeah, I will.
Just let me know once you've started and we'll start the session.
Yeah, the recording has started.
Okay, great. So I hope you guys have been enjoying Horizon Summer School so far. Hope you've had some fun sessions. So me and Ganesh will be conducting the next two sessions. This session will be on quantum physics and the next one will be a continued session on quantum computing. So yeah, and of course today's 15th. That's on us. So what we will be doing is we'll be introducing some basic ideas in quantum mechanics. And as I'm sure you're aware, we require a lot of math to do it. So we'll be introducing a lot of different math concepts, not very rigorously, more with the idea of you understanding the terms so you can learn it on your own later as well. And using this math, we will start forming postulates and try to explain a couple of quantum phenomena. Once we have this base in quantum physics, in the next session, we'll go on to explore quantum computing. So this is a quick view of the syllabus of what we're going to cover today. So first off, we're going to just see why quantum behavior is so unusual, so awesome, like a couple of thought experiments. Then, of course, I'm sure you've heard of the uncertainty principle. We'll mention that and see what that idea is again. And the Schrodinger's cat thought experiment, we'll talk about that. Then we'll go into linear algebra for some time. We'll introduce a lot of different terms. And once we introduce them, we will go into how we use linear algebra in physics, namely the Dirac notation. And once we do that, we will form a set of postulates that are used in general for quantum mechanics. And using those postulates, we will analyze something called spin. We will see what it is. It's something fundamentally quantum. There's no equivalent of spin in classical physics. So we will introduce those experiments and we'll come up with our own quantum system to explain what we see. And lastly, we will just hint upon something called entanglement so that you can have a flavor of what is going to come in the next session. All right. So let me introduce myself. I am Sai Subramanian. I am just completing my BSMS physics at IITM. And me and Ganesh are going to do this session. I'll start it off and then I'll hand it over to Ganesh for some of the linear algebra. And then I will finish by telling you about spin and multiple spin systems. All right, so let's go into exploring quantum mechanics. No prerequisites are assumed. I'm just assuming you know like high school math and physics, and all quantum physics will be introducing from the start. I'm aware that those who have completed their first year of undergrad at IITM have done some quantum physics in PH 102. And don't worry, only the first couple of topics might have a little bit of repeat. Once we go into the linear algebra and spin, I've confirmed that it's completely new. Okay. So first off, let's talk about a particular thought experiment, something called the double slit experiment. Might have seen this in waves. So firstly, the thought experiment is basically you have a wall, and before that you have another wall with two very small slits in it. So we will release particles or waves or electrons and these through a gun, and these can go through either one of the two slits and can land up at any point on the wall. We have a detector on the wall that can move up and down along the wall, and it will tell us like the number of particles that are arriving at each location. So with that we can plot like a probability distribution to see where the particles are likely to end up. All right, so that is the thought experiment. We first run this with bullets or any type of normal classical particles, and so these classical particles can either go through the first slit or they can go through the second slit and can end up anywhere. If they go through the first slit, they're a little more likely to end up above. So if the particles go through the first slit, the probability distribution we get for where they're likely to end up is P1, as seen on the graph. And if they go through the second slit, the probability distribution of where they're likely to end up is P2. And given their classical particles, they're equally likely to go through either P1 or either the first hole or the second hole. So the joint distribution of where they're likely to end up will be P1 plus P2. So that's just a nice smooth curve that we see in part C. This is classical particles. They either go through the first slit or they go through the second slit and they end up at the back. Nothing unusual, pretty standard. You might be wondering, why are we doing this? We'll see that when we reach electrons. So next we go to waves. So in terms of waves, oh yeah, also an important point, our detector can also makes a click sound depending on like how much amplitude hits it. So in terms of a bullet hitting it, it's always the same amplitude. Like whether the bullet, there's no half a bullet that goes and hits it, so to say. It's always one full bullet that goes and hits it. So you hear one clear click sound each time the detector sees a bullet. All right. So now we go to waves. So for waves, you can visualize sound waves or water waves, for example. And as you would have seen in high school, when we have waves going through two different sources, they don't just add up, they interfere. So suppose we close one slit, or suppose we close off slit 2, and then we let the waves travel only through slit 1, we will get a distribution that is similar to I1. As to, yeah, and the difference is I1 is not a probability distribution of where the wave is likely to end up. It ends up at all these places. It's an amplitude, like intensity distribution. And the detector, you can hear a varied spectra of noises depending on the intensity. It's not like the bullets case where you either hear one click or not. If it's at a place of like high intensity of waves, you hear a loud sound. If it's at a place of low intensity of waves, you hear a mild sound. So with waves, you can hear the whole spectra of sounds from very dim to like a certain peak. And similarly, we close off slit 1 and let the waves only travel through slit 2. We will get the distribution I2. So we can write I2 and I1 in terms of the square of the amplitudes H1 and H2. This is what we typically do in wave mechanics, and I hope you've seen this before. So what's interesting is if we open up both slits, we see interference between both the waves coming out of slit 1 and the waves coming out of slit 2. And because of this, we don't just get a sum of the intensities I1 and I2. Instead, we add up the amplitudes H1 and H2, and we get a distribution something like I12 when we take the amplitudes, the square of the whole amplitude. And the reason for this is there is interference between H1 and H2. So if, say, for example, at a certain location, like H1 is peaking, the wave is peaking, and the other one is in the other, like they're in two opposite phases, then what happens? They interfere destructively, and because of that, there is not much actual amplitude there. That is why we see this spiky graph in part C. Whereas in other regions, if both the waves have a similar phase, they both add up constructively, and we see a larger peak than we would if we just added the two intensities themselves. So that is how we end up with I12. I'm hoping you've seen this before in waves in high school. So this is again something we've seen, and you might be wondering why I'm doing this in a quantum mechanics class, and you'll see that very soon. But points to keep in mind, there can be an entire spectra of amplitudes from 0 to a peak, and it leads to interference, which leads to this cool graph that we see in part C, and that is waves. And we know that waves go through both the slits at the same time. If we release a water wave or a sound wave, it doesn't go through either slit 1 or 2, it goes through both, and the two slits act as new sources, and the waves from these two sources interfere. Okay, so, and the detector sees varied intensities. So that is waves. Now coming to quantum particles, let's say electrons. Now suppose we were to release the electrons through slit 1 and 2. What do you think would happen? We are usually used to seeing electrons as particles. So let's say we close off slit 2. We only open slit 1. Then we get a probability distribution P1, which is very similar to what we saw for the bullets case. it goes through the first slit and it has a probability distribution of ending up somewhere. And similar to the bullet case, we only hear one click. There is no variation in, there is no half an electron doesn't reach the detector. Either the complete electron reaches or no electron reaches. So we get a probability distribution of where the electron reaches. Similarly, we close off slit 1, we get P2, the probability distribution of where the electron is likely to reach if it went through slit 2. But if we open up both slits, we no longer get P1 plus P2 as the total probability distribution like we did for the bullets. Instead, we end up seeing the pattern that we saw for the waves, which is pretty cool. These are electrons. These are supposed to be particles. But we end up seeing a wave-like interference pattern. And that is because these are quantum particles. So you might have heard that quantum mechanics is like it shows both wave-like and particle-like nature. And this is what people mean when they say that. This is the wave nature that is seen. So the wave nature is it interferes like waves. So we can describe P1 in terms of a probability amplitude phi1 and similarly P2 in terms of phi2. And the combined probability amplitude is phi1 plus phi2 modulus whole squared. And very similar to the waves part, you will have an interference term, and that interference term leads to the graph that we see P12. But an interesting point to keep in mind is even though we see this P12 graph, a graph like waves, in the waves part, we saw that the detector would pick up a complete spectra of sound. Like it could hear like a small amplitude of a water wave coming in or a large amplitude of a water wave coming in. Here the difference is the detector only picks up an entire electron. It does not pick up half an electron, so you don't hear half a sound. So what we're seeing is a proper probability distribution. So in that sense, it behaves like a particle. It doesn't behave like a wave. A wave goes everywhere. Like if you release water through slits, it goes everywhere at the same time. But if you keep a detector somewhere, you only see the electron in one location. It does not end up in multiple locations at the same time. So in that sense, it behaves like a particle. But in the probability distribution we get, it behaves like a wave. So that is what people sometimes say when it behaves part like a wave and part like a particle. So suppose we make a slight modification to this experiment. That is, we watch the electrons as they go through the slit. So one key point is in the earlier one, we don't know which slit the electron goes to when we are trying to measure P12. All we have is a detector at the backstop and it tells us where the electron reached. So now we are changing that experiment and we are going to watch to see where the electrons and which slit the electrons go through. Again, we close slit 2 and we close slit 1 and we get P1 and P2. But now, if we have both slits open and we put a light source, what happens is these two probability distributions P1 and P2, they change. We get P1 prime and P2 prime. As in now, if we measure, it is no longer the same as the previous experiment, the one where we did not have a light. These two probability distributions change and we get P1 prime and P2 prime. And the interesting thing is it starts behaving like bullets again. If we just identify which slit it goes through, this probability distribution is changing and we're ending up with a behavior like bullets. You might be thinking it's the same experiment. How does it change? Well, the answer to that question is when we shine a light, we are emitting some energy, some photons onto the electron. And when it hits that electron, it is changing the electron's momentum. And because of that, its distribution of where it's going to end up changes. And so what we are seeing is this change is leading to it behaving like particles. And now if we look at the combined distribution, it once again behaves like bullets. We just add up the individual distributions of whether it goes through slit 1 or slit 2, which we know now because we are shining a light source. So now it behaves completely like particles if we identify which slit it's going through. If we do not know which slit it is going through, then it behaves like waves. We get the probability distribution that includes interference. And as crazy as it sounds, stuff like this happens. It has been tested time and time again. The only reason we are doing thought experiments like this is because we don't have to worry about the intricacies of measurement and other diffraction effects and stuff like that. And it's easy to visualize. But an equivalent of this and several other things have been tested experimentally time and time again. And these are the kind of results we're getting. And that's why we have so much belief in quantum mechanics as a solid theory of reality. So to go through what we saw again, so to summarize what we saw there, so these quantum events, let's say electron going through the slit, are described by some complex wave function phi, and the probability distribution is the square of the magnitude of these complex wave functions. When there are multiple events, the wave functions interfere and they give us a wave-like probability distribution for the combined event. So the two events are the electron going through slit 1 and the electron going through slit 2. If we let both of these combine, we get a wave-like distribution. As long as we cannot identify which event is occurring. If we can identify, when we start making an attempt to identify which event is occurring, we end up changing the probability distribution of each event and the result of the combined event to behave like particles. So there is no intuition or classical analogy I can give you to say this is like this, because there isn't. It is fundamentally quantum. This is how quantum systems behave. If this is the first time you're seeing this, then yeah, it is a lot to take in, but this is how quantum systems behave. I'd highly recommend reading the first chapter of Feynman Lectures Volume 3. The first part is inspired from that. And yes, so this is one example of a quantum phenomena, and this is what we are seeing. We will build the postulates towards the end. So just think of these as thought experiments to kind of show you what quantum mechanics can be. And now we will talk about something that you might have just heard in passing, another pop tale. So there's this Schrodinger's cat thought experiment that you put a cat inside the trunk of a car, and then there's a chance, and there is some sort of poison or something inside the car that may or may not kill the cat. So in classically, if we think of this, we'd say either the cat died or the cat did not die, and we can open the trunk and check it. So, but in terms of quantum mechanics, if this were, instead of a cat, if this was a quantum event, and we had these similarly sort of two probabilities, what we would say is, until we open the trunk, the cat is in a superposed state of both dead and alive. The quantum event is in a superposed state of both possibilities happening at the same time. And when we open the trunk or when we check which event has occurred, we push the state into one of those two. So we open the trunk, or it is only at that moment that the cat becomes dead or alive. It is not that the cat has been dead or alive the entire time. Realistically, if you had a cat and a poison in a trunk, it's been dead or alive for a while. But the thought experiment is trying to inspire what it would be like if in a quantum world, in quantum events. So in quantum events, if you had some quantum event and there are two probabilities and you don't check it, it is in a superposed state of both probabilities. But the moment you check it, it will fall into one of those probability states. And that is what we see. And one of the key ideas is, so the superposed state that I'm talking about, which means it is in a state of either dead or alive, and we don't know if it's dead or alive, that is an accepted, well-defined quantum state. It is not that we have to do some measurement and we have to find out what is going on, more information about the state. No, it is a quantum, well-defined quantum state, and we know everything we can know about the state. There are a lot of, most quantum states are states where we will not know everything in single quotes in a classical sense. We can only know certain things about quantum states, and if we try to know any more, at least we do a measurement, we actually change the state. We end up with a different probability if it's an event, and we change the state. So if we make a measurement on a quantum state, it literally changes to a different state where we know this event, but in all likelihood we will probably lose out on some other information. This is the inspiration, and this is the inspiration and sort of the idea of Heisenberg's uncertainty principle, that you cannot know everything about a quantum system, and if you try to make an attempt to measure something you don't know, you may end up losing some other information. So let us look at one more example, sort of. Let's see that. So we've already seen that electrons behave like waves. So a lot of quantum systems will have wave-like behavior. And let me just give you a small idea as to why uncertainty is more natural in waves than it is in particles. So we know also that light shows some quantum behavior. You might have seen light is made of a bunch of photons. The energy of a photon is h bar omega and the momentum is h bar k. It's okay if you haven't seen this. I'm just going to use the fact where omega is the angular frequency and k is 2 pi by lambda. Lambda is the wavelength. So if you've not seen it before, it's okay. Just take this momentum expression for granted, that if you have a single wavelength lambda, you have a single k value and you have a single momentum p. That's all I need you to know. So if you've seen this before, great. If you haven't, that's totally cool. Just one thing to remember: a single k value or a single lambda value, a single wavelength, if you take a wave of a single wavelength, it has a specific momentum. Okay, so let's go into our visualization. So let's consider one wave. So this one wave I'm calling e power ikx. You can call it sin x, cos x, something like that, if you're more comfortable with the real numbers. Although we will be using complex numbers a lot, it is inherently part of quantum mechanics. There's no real way to do quantum mechanics without including complex numbers. So this wave has a single wavelength. You can just see that it's a single wavelength wave that just goes around throughout the entire region. So because it has a single wavelength, like I said, it has a single momentum and we know the momentum of the wave. However, if we visualize this wave, we can see that its amplitude everywhere is similar. And so we cannot identify where the particle, where it would be, where its amplitude is. If we were to make a measurement on position, then and say this wave had to decompose, then its probability of being anywhere is pretty similar. So we have absolutely no information on the position of this wave. We know its momentum, but we don't know its position. It can be anywhere on this wave. So yeah, it's quite weird to talk about waves like this. Normally you think of a wave moving in time. I'm talking about a wave fixed in time throughout this entire space. And if we make a measurement on position, I'm saying it has to decompose into one of the particular points. Where it decomposes will depend on a probability amplitude, and that is uniform everywhere. If we assume that probability amplitude is described by e power ikx. Now let's consider a second wave. Let's say we have a wave that we know the position very well. So it just peaks at one region. Again, this is a wave fixed in space, fixed in time. Just this is the distribution across space. And we say it is something like this. If you've seen a Dirac delta distribution, some Dirac delta graph before, this is something like that. If you haven't, totally cool. Just a graph with a huge peak. And how would you describe this wave? So if you've done a little bit of Fourier analysis or just in general, we know that if we write a single wave, say some single e power ikx, it's just a normal wave. But if we write a sum of a large number of e power I different frequencies, e power ikx values, then we know that at non-zero x values, the phase terms, the e power ik phase terms, will lead to it cancelling out. But at x equal to 0, this e power ikx goes to 0, and we just get a sum of all the coefficients, which leads to the peak. So the way to describe this graph would be the function psi2. If you haven't seen the math, don't worry, just take this for granted, that the way to describe a wave with a single peak is to write it as a sum of many different waves of different wavelengths. So now we know the position of the wave slash, if it's a quantum particle, very well. But because it's superposition of so many momentum states, if we try to measure the momentum, it could go into any of these momentum states. So we have lost all information on momentum. So if you see that we try to describe a particle in terms of a wave, you can see how either we have to describe it, either we know the momentum pretty well, in which case the wave is spread out over space, we measure it, we don't know where it's going to be exactly, or if we try to describe a wave that we know the position very well, we end up losing all information about the momentum. We try to measure the momentum of this, it could end up being anything. So this leads to the uncertainty principle, as you might have seen it traditionally, delta x delta p greater than equal to h bar by 2. So this is sort of an idea as to why if we try to describe quantum particles in terms of waves and wave functions, we end up with something called the uncertainty principle. The way we write down the postulates for quantum mechanics in terms of waves itself naturally leads to the uncertainty principle. We don't shove the uncertainty principle into quantum mechanics, but it is true, it has been tested a ridiculous number of times and it always holds. Okay, so just to summarize what we've seen, we haven't built anything formally, so don't worry about the exact details. It's just to give you ideas about how quantum mechanics works and what you would see in quantum behavior. So we describe quantum events and particles by complex wave functions, and these wave functions will give us everything we can know about the state. Even with like everything we can know about the state, this is our complete knowledge. There is still uncertainty about certain aspects. We cannot know it all anymore. We have to give that up when going from classical to quantum mechanics. And then suppose we make an attempt to measure what we don't know for sure, that is the information we don't have. We end up transforming the state into a different state where we may have that information but at the cost of some other information. The example above being, suppose we had this wave 1 earlier, and we tried to measure the position, we could very well end up with wave 2 where we have lost all information about momentum. So that is what the fourth bullet point is saying. And the final one is, an event can occur in different ways, or a particle can be in multiple states, and this is described by a superposition of these different events and states. If you've seen electromagnetism, you'd have seen the superposition principle used a lot. It simply means that if you have like multiple accepted states, then a general state is the sum of a linear combination of all these states. Don't worry, we'll do the linear algebra for this after this, and you don't have to know that in prior. I'm just hoping you've seen vectors like the 2D column vectors on a graph before. That's it, we are assuming. And speaking of linear algebra, that is what we're going to move to right now. And that is going to be taught by Ganesh. So I will stop sharing and let Ganesh introduce himself and cover the linear algebra part. We can probably stop for a couple of minutes. If you have any questions, I can answer. If not, you can just take a few minutes, maybe till 11:08. You can just take a small break because 2.5 hour session. We don't want to continuously shove 2.5 hours in and confuse you. So I will stop presenting and answer any questions.
Yeah, once again, I will let them unmute their mics as well. Yeah, I think everyone can unmute their mic now. So if you have any questions, feel free to ask them.
Yeah.
So while you were showing, you showed two waves, right? One was C1
Yeah.
e to the power I, and one was the other function that you called.
Yeah.
You said that if we try to look at the first one,
Yeah.
it might have been connected to the second one. Like, what do you mean by that? Right?
Sorry, I didn't get the last part of what you said. I didn't hear the question part. We have the two waves and
So yes, I tried to look at the first wave to
okay.
find the let's say position,
Yeah.
and you say that we lose all the information about the momentum, right?
Yes.
And then, but if we have a equation of a particular wave, shouldn't we know the momentum of it? Like, if we suppose we try to find the momentum, we have
Right.
the equation of the wave, so we know the position. So we don't we have both
Not
of them?
not necessarily. So if you have, even in classical physics, if you have a wave like the second one that just peaks in one position, the way you would describe a wave like that is a superposition of waves of many different momentum. So classically, you will say that's it. I have these waves of these different momenta, and when you add all of these, you get the resulting wave. So that is what is also called the Fourier spectra. If you don't have not heard the term, ignore that. So that is classically. Quantum mechanically, if you have like if you have to write a wave as a sum of different waves of different momenta, and you make a measurement on momentum, we are forcing that to go into one of these momentums, like one wave of one momentum, because you're trying to measure momentum. You want an exact value for that. So then you go back to something like wave one, if that makes sense. Have I answered your question?
I have gotten a bit clearer, but not 100%.
Okay, let me elaborate. So the second wave, the wave that peaks at one location, there is no way to write it as a single momentum wave. Even classically, you cannot write it like that. the only way to describe that wave is you have to write it as a sum of many different momenta. So even classically, if you have a wave that peaks like this, and if you ask like what wavelength and equivalently what momentum this wave has, somebody will tell you it is a superposition of waves of many different momenta. But that is enough.
Yeah,
That is
okay.
complete information in classical mechanics. But in quantum mechanics, if you try to make a measurement on momentum, you can only say, you can say for sure, I have these momenta, and this is the probability of getting this momenta if I make a measurement. That information you will have. But you cannot say the momentum will be, say, 10. You can, if you know the equation of the wave, like you're saying, you can say, okay, I know the probability of momenta 9 is this, momenta 10 is this, momenta 11 is this, momenta 12 is this, and I can give a probability distribution. But you cannot know which number you're going to get unless you make the measurement.
Okay, so we won't get the exact, we maybe like a probability distribution, and then we
Yes.
find the X value or something
Yeah,
like that.
we
And
can get a probability distribution with our information, but we will not know what number comes out until we actually make the measurement.
okay, got it.
Yeah. Thanks for the question.
Yeah, someone else was raising their hand as well.
Yeah. Just
Yeah, hi, go
I
for it.
have a doubt. In the first thing that you showed an experiment similar to YDSC, right?
Double slit, yes.
Yeah. So if that wall was, if there were no slits on it and it was just a complete wall, then how would the wave function look like? Because there'll be quantum tunneling taking place also, right?
Yeah, I ignored the quantum tunneling for this part. If we make the wall thick enough except the slits, there'll be no quantum tunneling. If there is a quantum tunneling, it depends on the thickness of the wave, of thickness of the wall, sorry. And you will have some small portions, and you'll have to treat each point on the wall as a source and then calculate. That involves a lot more math and calculation, but you're right. If the wall was thin enough, then it'll lead to quantum tunneling.
Okay. Okay. Thank you.
Thanks for the question. Okay, so if you have more questions on this initial part, you can post it later. Me or Ganesh will answer them later on the group. And if you've not understood anything particular so far, don't worry about it. The next 1 hour linear algebra is going to be completely independent of this, and I will hand over to Ganesh to continue that.
Yeah, thanks, Ryan. I will take the linear part for now. Hopefully you can see my screen now.
Yeah, we can see it.
Yep. So, quick intro. I'm Ganesh. I just completed my first year here at IITM. I'm pursuing my chemical engineering degree, and I will talk a bit about the maths that you need for, whatever we are going to learn in the upcoming session, and even in the same session as well, which I will be taking after this. So it's I will not try to go into the very like itty bitty details. I'll just try to skim over everything. Hopefully you understand. If you don't understand anything, don't worry. Post your doubts, we'll answer it. And a quick note, there are many good resources on linear algebra online. So even after this session, you can go and explore them. And if you want, I can suggest a few at the end as well. And so we'll start with something called fields. Uh, you know, uh, Fields, you can just think of them as numbers. Fields are basically a set of numbers which follow a certain algebraic structure. What I mean by an algebraic structure, it means it follows a set of algebraic rules, namely the ones listed here, the 5 rules listed here. What they say, what these rules are, they are basically commutativity, and the first two are commutativity and associativity. They are, the very basic ones that you already know what they are. And you also have a couple more rules, and namely, the additive and multiplicative inverses exist in this set, and additive inverses and multiplicative inverses also exist in this set. So the reason why we would define, a set of numbers with a particular algebraic structure as fields is because There are some nice properties that come out of it when you define it in such a way. When you start looking at what vector spaces are, you will see how incredibly useful this set of definitions are. And for the examples include the set of real numbers and the set of complex numbers. Both form a field, and in fact, complex numbers is just the superset of the set of real numbers. So yeah, they follow these rules and they are examples of fields. And for addition and multiplication, it's just a usual notation, usual definition. There's nothing much to think about. And these, like I said, fields are basically a set of numbers which follow certain algebraic rules. So whenever you think of fields, think of it that way. We'll move over to what vector spaces are. A vector space is nothing but a collection of vectors. You know, each element of a vector space, you would call them vectors. In your usual physics notation, you would have thought of vectors as these pointy arrows that exist in space, and you can just move them around, and it will not affect its properties. But in maths, you can generalize vectors as just elements of vector space. And what a vector space is you define it over a field where these 8 different properties, so it's a lot of properties, but it's very similar to what we saw above for fields. Most of them are similar, commutativity, associativity, existence of addition and multiplicative inverses, additive and multiplicative inverses, and the identities as well. The most important thing that you must note here is zero must always be an element of this vector space. And this is a very important property that keep it at the back of your mind. We will use it over and over again. Zero should always be an element of your vector space. Like I said, the elements of a vector space are often called vectors. And your usual vectors, these are 2D vectors. If x is y, 2, 3, the column vector 2, 3, y is the column vector minus 1, 1. This is your usual sense of addition, scalar multiplication and stuff. And the zero element here would be just the 0, 0 vector, and 1 is just 1. Or uh, it might be confusing why it's written as a scalar, just a 1 cross 1 element here, but it's not much to think about. You can just think of 1 as a scalar here, not as a vector. And speaking of scalars, always remember that for every vector space, there's an associated field or scalars that you define it with. You need them because when you try to define scalar multiplication, you always need a field over which you're talking about the scalars. You're talking about the scalars, right? So, and like I said, vectors can be much more abstract than just these 2D column matrices and the 2D, 3D vectors that you're aware of. Were in not trying to be too abstract, but you can think of any ordered list of numbers as vectors. So basically, an n tuple of a row or column, you can think of them as vectors because they follow all the rules that we defined above. They follow element-wise addition. What elements are? There is components of these so-called vectors. They follow element-wise addition, and there are some certain rules for multiplication as well. We'll look at it eventually. And an interesting thing is, you can also think of functions as vectors. Basically, how you would see them is, I just said that vectors are, an ordered list of numbers. So if you think as function as being some value defined at each point on the number line, it will form an infinite tuple. It's an infinite list of numbers, ordered list of numbers, and you can think of that as vectors as well. And you can even think of polynomials as vectors. You can, for say you have 1 x, x square, x cube, and so on. You can think of them as components of vectors as well. For example, if you have something like e to the x, you can write its components out to be 1 times 1, scalar times the component 1, scalar 1 times x plus scalar 1 by 2 times x square, plus 1 over 3 factorial times x cube, and so on. It's an infinite list, infinitely long list, and they also follow whatever the definitions of vector spaces are. So we can call them as vectors as well. It might not make a lot of sense now, but think about it, and it is perfect. You will find that it's perfectly valid to define them as so. Moving on. Subspaces are basically subsets of vector spaces. The only key point is that the subset should also be a vector space, which means the subset also follows whatever properties that we defined above, addition, multiplication, not multiplication, those inverses and identities, and scalar multiplication, and so on. So, which means that zero is always an element of your subspace. So, whenever you choose a subspace, remember that zero should also exist in that. Otherwise, it doesn't follow the very definition of what a vector space is. So, again, a subspace is nothing but a subset of vector space, which is also a vector space in itself. Putting it mathematically, you would say that zero is if V is a vector space and W is a subspace, then zero belongs to W and it follows all these additive and scalar multiplicative rules. And for an example, your entire R2, the 2D plane, if you consider that as a vector space, you can think of your x-axis as your a subspace. The zero element is included and it follows all the vector space properties that we defined above. So the x-axis, the vectors on x-axis, you would represent them by something like this. It's a column vector with the y component 0 and x component to be any scalar, which spans, I'll come to what a span is. It basically generates the entire set of uh, vectors on x-axis. So it's a valid subspace of your R2 vector space. We'll come to what linear combinations are. This is something I think most of you are aware of, and it is very fundamental to whatever we are going to discuss next. So, linear combination is nothing but a sum of scalar times the vector, and you sum it over all the vectors that you consider. Mathematically, you put it something like summation of AI UI. AI is your scalar that you defined over your field where you defined your vector space, and UI is the vector. And the linear combination is that you sum all of these vectors, which in turn generates another vector. So we'll come to what a span is. So if V is generated by these UI vectors, you say that V belongs to the span of these UI vectors. So an example of this is you have your vector 2, 3. It is generated by a linear combination of 1, 0 and 0, 1. Basically, I hat and j hat. You scale I hat by 2 times and j hat by 3 times. And if you add them together, you get this 2, 3 vector. So yeah, we did this to understand vectors in terms of the xy components. There are multiple other ways to define a basis. I will come to sorry, I'm getting a little bit ahead of myself. I'll come to what a basis and span is. So basically can think of linear combination as generation of vectors from a set of few vectors, basically. Uh, so yeah, we actually come to span. So span is nothing but the all the vectors generated by a particular set of vectors. If you have a subspace or subset of vectors called S, the span of S would be the linear combination of all vectors in S. So, for example, if you have J hat and I hat, which you represent like this, 0, 1, and 1, 0, the linear combination, which is just C1 times J hat plus C2 times I hat, it adds up to C1, C2, which generates the entire R2 plane. So you would say that the R2 plane is a span of the vectors I hat and J hat. And something which generates this is called the basis. The if it for the vector space R2, you would say that the basis is nothing but I hat and J hat. It's also called a natural basis. There are other bases as well. We'll come to that. Yeah. So a subset S of a vector space is said to generate or span B if span of S is just B. The linear combination of all the vectors is just the vector space itself. Yeah. And there is a notion of linear dependency of vectors. It's important to define this because it gives us an idea of how these vectors really are oriented in space, and it has a nice geometric meaning to it. A linear will define what a linear dependence is. A set of vectors is called linearly dependent if there exists a non-trivial combination of scalars such that this equation holds true. So earlier, I defined the linear combination to be some sigma AI UI, right? So if there is a non-trivial way, a trivial way to add a particular set of things to zero is to define all AIs to be zero. So we don't want that. We want a non-trivial way such that these add up to zero, which basically means at least one of these AIs should not be equal to zero. So if this condition holds, we say that the set of vectors is linearly dependent. And obviously, if the condition doesn't hold, we say that they are linearly independent. An example would be the vector 2, 4, and 4, 8, the vectors. As you can see, the 4, 8, 4, 8 vector is just the 2, 4 vectors scaled by some particular amount. So, uh, sticking to this definition, you see that if you call this coefficient A1 and this coefficient A2, and you define A1 to be 1 and A2 to be -2, you see that the sum of these two vectors would be 0. So in fact, these two vectors are linearly dependent, and in in the in your general Rn vector space, you can think of if two vectors are linearly dependent, geometrically it means that they both are collinear, or you can just scale them and you would get the other. And for three vectors, for say, to call them linearly independent, you, the you can either define it to be a pairwise uh, it should be pairwise linearly independent as well as I'll come again. For three vectors to be linearly independent, it has to be pairwise linearly independent as well as the combination of any two should also be linearly independent from the other. So that's when three vectors are called linearly independent. This is a geometric way to think about it. And yeah, this is an example of linearly independent set. No matter how much you scale this vector, you will never get this vector. Try doing it, multiply it with a scalar c, and you can see that this never holds for any c. Yeah, so we have finally come to what a basis is. So like I mentioned above, if a particular set of vectors span a vector space, you call these particular set of vectors the basis of that vector space. For example, if you have your R2 plane, if you define I hat and J hat, using that as a basis or that as your set of vectors, you can scale them individually and basically you can generate the entire R2 plane just by the linear combination of these two vectors. So to define an entire plane of vectors, that's an infinite set of infinite number of vectors. You just need two vectors and you're the field over which you define it, which here is just your real numbers. So if you do that, you can generate your entire R2 plane with just two vectors. You call these two vectors the basis of the vector space. The basis of R2 is zero, the I hat and J hat. There are many other bases as well. Basically, any two linearly independent vectors can span R2, which means any two linearly independent vectors can form a basis for R2. They can generate entire R2. 1, 0, 0, 1 is which I had in GAT. They're special because they are very nice. There's no scaling factor and it's very easy to work with them. So it's often called your natural basis or your standard basis or your canonical basis, which means it's your standard stuff. IAT and JAT are often called so. And moving on, there is a notion of dimension that comes into play when you talk about basis. So a dimension is nothing but your cardinality of your basis set. So if your basis consists of a finite number of vectors, it's basically which means your basis has uh, finite number of vectors. This set has a set's cardinality is finite. So you call that vector space to be finite dimensional because it is generated by a finite number of vectors. For example, R2 is generated by any two vectors, any two linearly independent vectors. So you call the R2 to be finite dimensional, and in fact, the dimension of R2 is 2. Similarly, the dimension of R3 is 3. R3 is generated by any three non linearly independent vectors. So all these conditions are equivalent. I'll pause here for a bit. We are moving on to some a new territory. Up to this point, many people would have learned this in the first year courses or even in frankly in high school as well. But this is something which might be new for everyone. So I'll take a quick pause here for 2 minutes, and if you have any doubts, just let me know. You can either type it in the chat or feel free to speak up. I guess there is none. So let's continue. A linear transformation. It's also called a map. It's also called an operator. This is a scary terminology. But essentially, what this all means is that it's an operator, a map, a transformation, or even as you get to learn more math, there's something called morphism. Basically, what they mean is they eat some input and they spit out some output. That's what they really are. Everything is just function, map, they're just all the same. And linear means it obeys certain properties. If you look at what they are, so a linear transformation or map is nothing but a function that eats a vector space and output spits out another vector space. It's a map from one vector space to another vector space. Um, if T is your function or your linear map, it maps your vector space V to W's, and it maps in such a way that it obeys certain properties. These properties are what makes this transformation linear. The reason why we have this is uh, due to this linearity, there is a lot of stuff that is easy to visualize and um, nice properties that come out of it, which we can easily exploit. Uh, so, if you recall, I mentioned that for a basis spans the entire vector space. So, for you to define a transformation from one vector space to another, it's just enough for you to define how the basis vectors transform. If you just know how the basis vectors transform, you know basically all information about the vector space, right? So this is essentially what a transformation looks like. This is enough information to say where the entire planar vectors land on all the 2D vectors. So what this means is you basically represent this as a block of numbers that is a matrix. What this means is this column This column says where the basis I hat lands, and this column says where the basis j hat lands. So if you know where they transform into, you basically know where all the vectors transform into, because basis contains all the information about your vector space. So what this means is your I hat lands onto I hat itself, it doesn't change, and your j hat lands onto 2 comma minus 1, the 2 minus 1 vector. So when you with this information, if you want to find out where any other vector in R2 lands on, you just multiply this transformation with that vector. It's basically, if you see it, it's like applying a function to your input. This is your function and this is your input, and it spits out where it lands on. So it eats a vector and spits out another vector, which says where this vector has landed on after this linear transformation. So this, if you just put T here, you can see that it's just matrix multiplication. As to why it is a matrix multiplication, there is a nice intuitive meaning to it. I will not go into those details, but I will recommend some resources at the end of this session, or end of this part anyway. So yeah. So examples of for your 2D vectors, your linear transformation would be a 2 cross 2 matrix, and for your 3D vectors, it would be a 3 cross 3 matrix. It maps your 2D plane into another 2D plane, and your 3D plane into another 3D plane. But those are the transformation basically results in some sort of scaling or rotation and stuff like that. That's a geometric way to think about it. That also is due to the fact that this transformation is linear. If you don't have them linear, there are much more things that could happen, and there is no nice way to define it. So, very nice things come out of defining it to be linear. Like, you can think of these transformations as scaling and stuff. And there's a particular theorem called the singular value decomposition. It says that any transformation is just scaling and rotation by some sort. Uh, I will probably cover that in session 2. And it's all there's a nice geometric meaning to all of this. And I would highly recommend you to explore this after this session. Yeah, like I said, a linear transformation can be represented as a matrix, but for it to be represented as a matrix, you need that to be finite dimensional. Like I said, for the information to be contained, the information about the basis to be contained in this matrix, it has to be finite dimensional. Otherwise, you'll have this infinitely huge matrix, basically infinite cross infinite matrix, which is of not much use. So we restrict ourselves to a finite dimensional vector space so that this transformation matrix is also something finite. And coming to coordinate vectors, there's nothing much to it. It's just your usual position vectors that you think about. Each your vector, you can think of them as a column with components as their elements. And this basically means where if the components basically identify where the vector is or the point is respective to some basis. This is very dependent on the basis. When you change your basis, the way you represent a particular point in your space also changes. So the numbers here will also change. So take care of that. Any point in the R2 plane, you can represent it as a position vector as such. So you need, like I said, you need a basis. You need here you have your I hat and G hat, and with that you can define any point on your R2 plane. A and B are just numbers here, the real numbers. Yeah. This is probably very new to many of you. There is something called a dual space. For every vector space, there's an associated dual space. So what this dual space means is basically we thought about linear transformations as something that maps vector space into vector spaces, and it transforms vector spaces into another vector space. So, but And when you look at this matrix, it's also possible for you to map your vector space into just a scalar, just a number, the field over which your vector space was defined. So how we would do that? If you recollect, your column vector is just your 2 cross 1 matrix, and if you multiply that by a 1 cross 1 matrix, 1 cross 2 matrix times a 2 cross 1 matrix, it would result in a 1 cross 1 matrix, which is just a number. So a linear, as you would call it, a linear functional. A linear functional is nothing but a linear map that maps your vector space um, into a field rather than another vector space. And thinking of it geometrically, I'll try to draw a quick figure. Hmm, I think I can do it here. For example, you have your R2 plane here, and you have your this number line. So this is your 1D number line that you wish to map on. And sorry, but this has to pass through the origin. Remember that every subspace has to contain the origin. So yeah. And for example, you have a bunch of vectors, and you wish to map them onto this number line. Basically, that's what a functional linear functional does. It maps your vector space onto your field or a number line or 1D, whatever you like to call it. And if you see, mapping it would just basically do something like this. It maps this vector to this point, this vector to this point, this vector to this point, this vector to this point. And some of you may notice that this is very similar to taking a dot product. And in fact, a dual space can be defined using a dot product. They are actually equivalent to each other. Linear functional in 2D is nothing but taking the dot product, because your dot product follows these properties of vector space, that is properties of linear transformation. It follows these linearity properties, which essentially makes dot product your linear transformation for Rn. But for now, we'll talk about R2 only. So we can linear functional of R2 will always be a dot product. It will essentially be a dot product. And what a dual space is uh, your span of all is a space of all your dual vectors. Your dual vectors is nothing but your dot product operation. And like I said, it will be a 1 cross 2 matrix. And if you multiply with a 2 cross 1 matrix, it will spit out a number, which is basically a 1 cross 1 matrix. So for this vector, you would call this associated operation the dual vector, and the span of all these dual vectors, you call them the dual space. Call that the dual space. So for every vector space, there is an associated dual space. And if you if you actually notice something, we'll come to an example later. If you notice, or if you have a vector or a vector like a1, CD, your dual vector would actually be CD just written this way. The reason why it's so symmetrical and it just looks like you're just taking the transpose of the matrix, it arises from something about it arises due to the symmetry of dot product. You can explore more about it later. The keyword is dot product is symmetrical, basically. Your A dot B is the same as B dot A. So this symmetry is something that comes out of the dot product definition. And of course, dual spaces are much more general than this dot products. In your Rn vector space, you can think of them as dot products, but it is excuse me, it's better to make them more general and go beyond just thinking of them as dot products. And we'll come to what a dot product is now. Yeah, this is the definition of dual space. I think you can read it. And there's a certain mathematical formalism to this. Your dual, if you have a dual space, it follows these properties of essentially, if you recall, if you have your ij and if you consider the dual vectors like 1 0 row and 0 1 row vectors, if you multiply one with the other, basically the dual vector of I with the vector j, you will get 0. So, which essentially is an orthogonal condition. An orthogonal means perpendicular of some sort. So, there is a bit of formalism to this, and this is usually represented by del ij. It's a Kronecker delta symbol, which is nothing but when I is equal to j, this equals 1. Basically, when you apply I with its own dual vector, it results in 1, and if you applied it with any other dual vector, it will give you out it will give you out 0. As an example, consider the basis j and I and a vector v just to 1. So your dual basis would be the row vector 0 1 and the row vector 1 0 0. Something like taking the transpose of it. And I mentioned why it turns out to be the transpose. It has something to do with the symmetry of dot product, and I would suggest you to explore it. It's very interesting. It was very fascinating for me, at least when I learned about it for the first time. And yeah, and your dual vector would be just v star. And yeah, the notation is basically putting an asterisk next to it. The dual vector of v would be represented by v star, and it is same as taking the transpose in this case. Yeah, we come to inner product. And inner product is just a generalization of your usual dot product. I think many of you would be aware of what a dot product is, and it's important to generalize stuff like this because vectors are not just limited to your usual R2 and Rn stuff, and it's much more abstract and general than that. So you define an inner product with the operation. You define it with something with the angular brackets. Basically means an angular bracket of two vectors. It's an operation that occurs between two vectors. Um, so the inner product of x y is nothing but the element-wise addition. Um, it's a bit more than that. When you deal with complex numbers, you have to deal with the complex conjugates as well. We don't have to worry much about that for now. Essentially, they follow these it's important to note these properties. I will go over again what the definition is, just to be concrete. An inner product on V is a function that assigns to each pair of vectors a scalar in F. It's also a map that maps just like dot product. It is the dot product. It's something much more general. It maps your vector space onto its associated field. So, and the meaning of this geometrically is nothing but uh, your dot product, which is just projecting one vector onto the other. So the dot product is an example of inner product. And like I said, both these definitions are equivalent. Dot product, your linear functional, that is dot product, is uh, is the same as dot product when you're dealing with Rn. So you have your vectors v1 and v2, and the dot product is nothing but a1 a2 plus b1 b2, the element wise addition. And if just like we did a while ago, yeah, like I did, yeah, I think I raised it. This is nothing but the same as multiplying the dual space with each of its vectors. So you have your dual space here, 1 0 and 0 1, and if you multiply that with your vector space, you basically get something that is the same as what you would get when you deal with when you have done dot product. So it just goes on to say that the dot product is the same thing as um, finding the linear functional for Rn. Again, what a linear functional is just something that maps your vector space onto a field rather than another vector space. It's also called a linear norm, and yeah, just keep that at the back of your mind. So there is something called norm that comes with when you define what an inner product is. A norm is nothing but you perform an inner product with the vector itself, and the square root of the inner product of um, the vector with itself, and it's denoted as such. And the geometric meaning to it is when you define a particular basis and compute this, in your usual Rn is just a distance from your origin to that point. So that's the geometric meaning for this, at least in your Rn. Okay, but just to be clear, when I say Rn, I just mean R to the n. Okay, so hopefully I didn't confuse you before. Yeah. And these are a couple more terms that I would like to define. So a vector is said to be normal if its norm is just 1. If its magnitude is 1, like I said, the distance is the magnitude of the vector. So if the magnitude is 1, you call that vector to be normal. At least this definition holds in Rn. Again, I want to emphasize this, whatever geometric meaning that I give to all this, it only holds for Rn. When you deal with complex stuff, when you deal with C to the n, it is something more abstract, and there is nothing, you lose the geometric meaning when you do that. So it's when you learn all this stuff for the first time, it's useful for you to just stick to Rn so that there is you can associate it with your with a geometric meaning so that you remember it. Again, what will come to something called orthogonality. So a set of vectors is said to be orthogonal if the inner product of each pair of the vectors from the set is 0. So if you have two vectors v1 and v2, you call them orthogonal if the inner product is 0. Again, in Rn, when the inner product is 0, and when the inner product of two vectors is 0, it just means that the vectors are perpendicular. That's a geometric way to think about it. So in your Rn, whenever you encounter the word orthogonal, think about them as perpendicular vectors. And orthonormal is just your extension of orthogonal. When the norm of each vector is 1, you call that orthogonal set an orthonormal set. It's both orthogonal and normal, so call it orthonormal. And for a set, it is you can define orthogonality for much more than two vectors. You can define for a set of vectors, and a set of vectors is called orthogonal if it is pairwise orthogonal. Each pair is also orthogonal to each other. In that case, you call a set of vectors an orthogonal set. And so this similarly the same for your orthonormal. Uh, Now we move on to something called the Dirac notation. I think it's the right time to hand it back to Sai. He will give you a much better understanding of what all this is, and hopefully this you understand all this with the stuff that I just taught. And from here we'll build it on to what spin is, and we'll move on to the actual quantum computing stuff. So Sai, I think I'll hand it back now. And if there's any more questions, you can just ask them. We'll have a small break now.
Thanks, Ganesh. Yeah, we'll take a 5-minute break. You can
Yeah.
ask any questions about the math so far. And I just mentioned that you don't need to remember everything in detail of what we covered. We know we've covered a lot of math. A lot of it might be new. So don't worry at all. Whenever we're using some of it, I will keep reminding you. And we just want you to know this terminology because it is what will be used if you try to read a quantum mechanics textbook after this. They will use all of this terminology, and this terminology expands a lot more than just the 2D column vectors. It can apply to functions, it can apply to polynomials, it's used in machine learning, it's used everywhere. So that's why we define it in a general sense. But all these ideas and intuition is built from like very simple stuff that we studied. The simple 2D vectors is a nice example for that. So I'll take a 5-minute break, and any questions you have, you can ask.
I think I missed a question in between in the middle of the session. Someone asked what's the transpose of it. Can you just ask it again? I think you can unmute your mic. Oh, okay. Yeah, if there are any more questions, you can feel free to ask them. Oh yeah, and the resources, most of this geometric meaning to all this linear stuff, I learned it from Three Blue One Brown. I think most of you are aware of this channel. So his essence of linear algebra series, it's very good. It's like one of the best things that ever exist on the internet. So I recommend you all to watch that. It's very interesting, and it basically shows how intuitive and uh, uh, intuitive and geometric everything is. And I highly recommend you to watch that after this session. I'm pretty sure you can find it on YouTube. If not, I will also send the link. It's Three Blue One Brown. I will send the link in the group after the session. So don't worry about it. Yeah.
Don't worry, we will share the slides after. And in terms of going overhead, I can do one thing. I will just mention to you again all the terms and just the 2D vector examples of them, like a quick 5-minute recap before I start. And don't worry, by using the terms again, I'll just remind you if you forgot. We understand like this is a lot, and nobody would be able to follow everything for the first time seeing this. The reason we just mention all these terms is because these have a general meaning. We could have just said, okay, these are your 2D vectors, this is your dot product, and this is the like dual vector and everything. But the same thing holds for functions, the same thing holds for polynomials, and that's why we mentioned it generally. But for now, for the rest of the session, we'll mainly be working with column vectors only. So I'll just mention each terms like name, and I'll just give you the example in 2D vector space. So for the rest of this session and most of next session, you'll just need that much. Is that cool? But yeah, like Ganesh said, it is very interesting to go into the linear algebra aspects of it, and it's used everywhere. Like I mean, everywhere in all of science and engineering. Cool. Ganesh, can you stop sharing? I'll share and continue. Thanks, Ganesh, for the
Yes.
math. We need a lot of this linear algebra now. Okay. Okay, am I audible and is the screen visible?
Yeah, it is visible.
Okay, so yeah, the next 5 minutes, just a quick recap. What are the definitions we saw and an example in normal 2D column vectors. And after that, we will move on to the actual quantum mechanics. Okay. So fields. So fields for us is just a set of numbers. There's a set of real numbers, or most of the time we'll be using the set of complex numbers. Okay. So if we say fields, it's just a set of complex numbers with normal complex number addition and multiplication. We may call them fields. We may call the each individual number as a scalar. Scalar or complex number, same thing for us. Okay. So vector space, the set of all vectors that we're going to be using. So if we use 2D column vectors, it is all of the 2D column vectors. That set is called a vector space. Okay. And we have standard vector addition and vector scalar, like scalar multiplication of the vector. If I say 3 times a vector, you know what I mean. So the same thing. Then subspaces. Subspace is something within a small portion of a vector space, but it in itself is still a vector space. So in our 2D space, like normal plane, if we just take the x-axis or we just take the y-axis, that will be a subspace. So linear combination, we're just writing one vector in terms of a combination of other vectors. It's just like writing a vector as ai cap plus bj cap. If we do that, we can understand all vectors in terms of just like a couple of vectors. Span is just a set of vectors that, like if you take one or two vectors, all of the vectors that you can cover using this linear combination idea. So if you take I cap and j cap, you can cover all 2D column vectors. So that is called span. We're saying these vectors span all these vectors. So if you know how I cap and j cap behaves, you can visualize how every vector on the plane behaves. So that is span. Okay. Yeah, and that's why we say if a subset spans the entire space, we say, yeah, if a subset has a span equal to the entire space, we say it spans the entire space, just language. So if I say I cap, j cap spans the entire space, I mean I can write any vector in terms of I cap, j cap. And linear independence, it means that one vector is not just a scalar multiple or like a sum of other vectors. So suppose I take I cap and 2 j cap, 2 I cap and 2 I cap. I do not need to learn about 2 I cap separately. Just knowing about I cap is enough. As I cap and 2 I cap are linearly dependent vectors. If I take I cap and j cap, I cannot learn about how j cap behaves using I cap. So these two are linearly independent vectors. It's just that we need like as many linear independent vectors to understand the space. If I have I cap and j cap, I will not need I cap plus j cap. I can just understand them in terms of I cap and j cap. And basis is the set of vectors that we are using. So I cap and j cap will be called a basis. We can use different bases. I could have used I cap plus j cap and I cap minus j cap as my basis. Definition is the number of vectors in a basis. So for us in a 2D column space, the dimension is 2. That's why we call it 2D column space. Then linear transformation or operator or map, we are just going from one vector space to another. So think of them as matrices for us. We have like a 2 by 2 matrix will take us from one like 2D space to another 2D vector space. So for us, they are essentially matrices. In general, they can be a lot more, like particularly in functional space and all. But for us, just think of them as matrices. Then coordinate vector is just that when we write something as a I cap plus b j cap, this a comma b is our coordinate vector. It's just given a name. Again, language, something we're used to. So vector space of linear transformations, just it means that these linear transformations themselves are vectors. So you can treat matrices like vectors. Not relevant for us now. Might be in next session. I'll see. If that is, I'll cover this again. So dual space is basically for us, if we take 2D column vectors, the dual space is the 2D row vectors. It's basically, we want to go from vectors to the numbers. When we take a dot product, we want to write this as an operation. So we use the dual space. It might seem stupid, why not define the dot product? But it has a lot of general use in physics. We'll define something called an outer product also later, and all of that dual space is very useful. So if you think of dual space, think of for column vectors, row vectors. And dual basis is just the corresponding basis that maps to conjugate. Just think of it, if we have I cap, J cap here, then it's the same in row vectors. So if it is 0, 1, 1, 0 column vectors, then our dual basis is just 0, 1, 1, 0 in row vectors. So then we can define something called a dual vector. So it means if my vector is the column vector 2, 1, my dual vector is the row vector 2, 1. Just to define that, we have the dual basis. And inner product for 2D column vectors is basically the dot product. We want to go from vectors again to like scalars, and that's why we write it in terms of the dual vectors. I'll come to that, sorry. So inner product, like dot product. So if you take inner product of a vector with itself, we get its norm, like the magnitude of the vector. We take with another vector, it's like taking A dot B. We want to know how much of one vector is on the other vector. Very dot product idea. It's going to generalize. And yeah, this might seem like the most unnecessary bit of math, but it is not. You'll see in a bit. So taking dot product is the same as multiplying the dual vector. So if I write a1 I cap plus b1 j cap and b2 as a2 I cap plus b2 j cap, dot product is just a1 a2 plus b1 b2. You've seen this. But we can also write it as a1 times the dual vector. Like we can just write b1's dual vector first, and we can write b2 as the vector itself and multiply them out. We get the same result. So taking dot product is nothing but multiplying with the dual vector. That's why we define the dual vector, and you'll see Dirac notation in a bit. And yeah, so that is a recap of the math we did. Quick recap. Don't worry, I'll remind you of the terms if needed, but I hope that's a bit better, like for now, for the session. But all the general stuff that Ganesh covered, it is very interesting and has a lot of applications. So yeah, if you're interested, look into it later. For us, we will mainly be using we'll just be shifting from real to complex space. That is all the transition we're going to be doing, and I'll walk you through that. So Dirac notation, complex conjugate, you would have seen. So our normal vector space, all of the vectors we will be writing as this ket. So just give me 1 second. Yeah, so this ket is how we'll be writing a vector. And when we have a vector, this is going to be a dual vector we're going to write, and this is called a bra vector. Yeah, physicists use some funky terms. Yeah, so like we discussed, the inner product between two vectors is nothing but multiplying the dual vector with the vector. So that is why we define this symbol like this. Dual vector and this vector multiplied together. This is the symbol for inner product. Okay. Tensor product we will be covering the next session. It is not relevant now. And the other stuff is just matrix terms. Matrix terms that you might have seen before. Complex conjugate of the matrix. Just a complex conjugate of all the individual elements. Then transpose of the matrix, and Hermitian conjugate or adjoint is nothing but you take complex conjugate of all the elements and then transpose the matrix. And the last one, inner product between phi and a times psi. So sometimes you will operate on a vector and then take inner product. So this is nothing but saying, say, I am defining some vector theta as a times psi. This A is some matrix. I'm multiplying matrix with the vector. I'm getting a new vector, and then I'm taking dot product of phi with theta. So instead of writing this, defining this new vector and then writing it, we can write it like this. We can just write it as phi a psi. It means we're operating a on psi and then taking dot product or inner product with phi. Okay. So that is Dirac notation. You might be thinking, why so much hype about this? Just a bunch of like notation, but it is really powerful later on. Okay. So we'll now move on to the postulates of quantum mechanics. This is the ideas we will use whenever we try to describe any quantum system. And yeah, so first, Hilbert space is a complex inner product vector space. What that means is it's a vector space with the field as complex numbers. So if you take a 2, 1 column vector, it means that each element will be a complex number. It will be z1, z2. It will not just be two real numbers a, b. And we have defined some inner product on it. So the complex inner product will be very similar. I'll define it later. But you define something called a complex inner product on a vector space. We have a vector space. The field is complex numbers, so all our elements are going to be complex numbers. Our scalars are going to be complex numbers. And we define something called a complex inner product on this. So when we do that, in general, we have a Hilbert space. Once we have a Hilbert space, we define the dual space. And the dual space and the complex inner product will be one-to-one mapped. Once we do this, we have like the space of all of the states of a quantum system that we can possibly have. Then we define a given state psi. Okay, so we write it as a ket vector, like the Dirac notation said. So nothing, Hilbert space, vector space with a complex inner product. And then we define an individual vector in it. And this vector will evolve over time through the Schrodinger equation. We have skipped through the, like there is no actual derivation for the Schrodinger equation. You can motivate it from the wave equation. But given we're going to do quantum computing, we skip that instead to do spin. And I think you will enjoy spin. So I'm just mentioning this because I didn't want to take a lecture on quantum mechanics and not mention the Schrodinger equation. But it basically tells you how this wave or how the quantum system will evolve over time. If we understand that and we write that down as an equation, that is called the Schrodinger equation. So for general systems, it's all about finding the Hamiltonian operator. So that tells you how a system is going to evolve over time. We will not be using this too much today. We might use it a bit in the next session. But then also we won't use it in this state. Okay, so this is what we saw earlier formalized. So when we make a measurement or something like that, or when we have like several different states or several different outcomes, like say multiple slits, for example, or dead or alive, we'll call these different outcomes omega I, where I can be like 1, 2, say slit 1, slit 2. Omega 1 can be dead, omega 2 can be alive. So then we can call these states as in the ket notation omega 1, omega 2. So what that means is omega 1 means electron went through slit 1. The state omega 2 means the electron went through slit 2. Or omega 1 means the cat is dead. Omega 2 means the cat is alive. Then if we want, then we have a general state psi, and we want to find out the probability amplitude of a given event. We will take inner product with that event. So if the state where the electron is in the first slit is omega I, then we take our general state psi and we take inner product with omega I. That is how we find out what is the probability amplitude for the electron passing through slit 1. And if we want the probability, we take magnitude of that and square it. So this inner product of psi with omega I is what I would have written there as phi a lot earlier. So we define all the possible states and outcomes, and we take inner product of our general state with that. So we're saying how much, that's why it generalizes from dot product. We're saying how much of this amplitude is in this event to find the probability amplitude. So that's why inner product is like dot product. If you think of a general, if in 2D space, if I give an example, if you think of the I cap plus j cap vector and you want to find out what is its like amplitude on the I and j axis, you will take dot product and say it is 1 by root 2 and 1 by root 2. So something like that. But here we're working with probabilities because it's quantum mechanical. So yeah, when we make a measurement, what happens? We change the outcome of we change the system itself. So suppose we make a measurement now and we find out whether the electron went through slit 1 or slit 2. After we do that, the new state of the electron is no longer psi. It is now omega 1 or omega 2. And the probability whether it is omega 1 or omega 2 is given by P1 or P2, which is the magnitude of the probability amplitude square. So suppose, say for the cat is dead or alive example, let me go through this. So the outcomes are dead and alive. The two states are cat dead state, cat alive state. Our general state psi is a superposition of both dead and alive. So then if you take inner product with dead and inner product with alive, then you will get the probability amplitudes for the cat being dead and alive. And then if you take magnitude of that squared, you get the probability of the cat being dead or alive. Now, if you make a measurement on the cat with the probabilities that you find, the cat will either become dead or alive. So now the new state of the cat is either dead or alive. So omega 1 or omega 2. It's no longer the superposition state. So that is in general how quantum mechanics measurement will work. Okay. This is like not very formal way of mentioning the postulates. Might think this is just explaining two simple thought experiments, but this is the way you will build any quantum system. Be it a complicated one, be it some sort of quantum well, be it some quantum harmonic oscillator, any sort of system. This is how you will define. You'll try to find the Schrodinger equation, the Hamiltonian, see how the state evolves, and you'll see what happens when you make different measurements. Okay, so this is the postulates. Now we are going to address something very specific, something that has no analog in classical systems. Quantum spin. I think you might have heard of spin when we were studying like atoms and the different like electron placements in the different shells. You might have come across something called spin quantum number. So you can say that in each shell in like S, you have two electrons. One electron is spin up, one electron is spin down. So that is the spin is something we're talking about. It is only there for like quantum particles. It is, we don't talk about this classically. So what spin is, it is an inherent quantized angular momentum. What it means, the electron has some angular momentum. It is quantized. It means it is either like h bar by 2 or minus h bar by 2. I am just going to stop mentioning h bar because it just makes it more complicated. Think of it that we're working in units where h bar is 1. So I'm just going to say spin half or spin minus half. So if you take an electron and you measure its spin with respect to some direction, you will get either plus half or minus half. That is spin half particles. There are also other spin particles, but that's the idea. It has some quantum, it has some angular momentum, even if it's sitting in one place. Normally, you think of angular momentum when the electron is moving and it's moving in a circle or something. No, even if the electron is sitting in one place, it has some angular momentum. Like some people like to visualize it as the electron rotating around an axis, but that is not true. That is not at all true. There is no actual visualization for this. It's just a fundamental fact that has been measured a lot, that the electron has some natural angular momentum, even if it's sitting in one place, and that is called spin. We will do some thought experiments to see how the spin is not classical, how it is something completely new and amazing, and we will be able to actually build a like a mathematical system to describe what will happen, and we can actually calculate and predict what is going to happen to the spin. We're going to build that using the postulates and linear algebra that we've done. So that is the plan for the rest of the lecture. So we're going to focus on spin half particles. So if we measure the spin, we will either get plus half or minus half. When I say measure spin, I mean in a particular direction, say the z-axis. Then it will either say plus half, the spin is pointing up on the z-axis, or it will say minus half, the spin is pointing down on the z-axis. So there's something called the Stern-Gerlach experiment. So the way the experiment actually works is not relevant to the ideas we're going to discuss. So that's why I've written it like a thought experiment, but it's a very real experiment that has been done. So basically spin has some, if there is spin, there's some angular momentum. That angular momentum leads to a magnetic dipole moment. And because of the magnetic dipole moment, you can put a magnetic field. And you can separate whether it's spin plus half or minus half. So for us, we don't need to know how it happens. Just think of the Stern-Gerlach apparatus as something like this. You put a beam of neutral spin half particle, neutral again because you don't want the electric field and like charge moving in a magnetic field effects. So neutral spin half particle, if you put it in a Stern-Gerlach apparatus, it splits into two beams. The beam with plus half and the beam with minus half. Okay? And this is in a particular axis. You can make the spin half measurement in the z-axis. We're going to use all three axes, y-axis or x-axis. Okay? So if I say SZ, it means I'm putting a Stern-Gerlach apparatus that measures the spin in the z-axis. And in that axis, you will find that the beam, if you have a beam of a lot of particles, some like about half of them, if they're like not biased or anything, half of them will become spin up, half of them will go into spin down. And sometimes we will block some of the like a particular spin particles and analyze just the other ones. So we know what spin it has. And we will see quantum mechanics in its true beauty now. So I hope the Stern-Gerlach apparatus is clear. Just recapping one more time. Throw in a beam of particles. It will split into two beams. The beam with the spin plus half particles and the beam with the spin minus half particles. That's all we need to know, okay, about the Stern-Gerlach apparatus. We have three apparatuses. Think of it as three black boxes. We have Stern-Gerlach in the Z, Y, and X axis. So it will measure, it will and split this beam into spin half in the z-axis, the spin half in the y-axis, spin half plus half and minus half in each axis, depending on which apparatus I put. So we are going to run some thought experiments now with this axis. The reason I say thought experiments is to skip over all the details of measurement and like other movement that can happen, but it's a very real measurement that is done, Stern-Gallasch. If you're interested in actually how the measurement is done using the magnetic field and stuff, you can Google this. So for now, we will think of the thought experiments. So let's say we take a beam of neutral spin half particles, put it into a SZ, Stern-Gallasch in the z-axis. Half the particles turn out to have spin half, about half, 50% of them turn out to have spin minus half. And now we block off the spin minus half particles. We are only interested in the spin plus half particles. Okay. So we take this beam of spin plus half particles and measure the spin in the z-axis again. And all of them come out to have spin plus half particles. And that is something you'd expect. So we had spin plus half before, and we are only taking those and we're measuring spin in the z-axis again. So naturally, as we'd expect, all of them have the spin plus half. So next, let's do a second thought experiment. Let's measure the spin in the x-axis first. So again, when we measure in the x-axis, since these are just random particles, they're not biased or anything, half of them turn out to have spin plus half, 50%, and half of them turn out to have spin minus half, 50%. Now we take only the particles with the spin plus half in the x-axis, and we try to measure their spin in the z-axis. We can see that half of them end up having a spin plus half in the z-axis, and half of them end up having a spin minus half in the z-axis. Again, so far, this is something we would have seen if spin is just a classical vector as well. Components can be anywhere, and then you get like 50% chance. But let's move on to the next thought experiment. So now we are giving all three directions. So first we measure spin in the x direction. Again, 50% end up with plus half, 50% end up with minus half. And now we measure spin in the y direction. Again, 50% end up with plus half, 50% end up with minus half. And remember, this is all spin minus half in the x direction. So what it's saying is whether you take spin plus half in the x direction or spin minus half in the x direction, it is not affecting the y component of spin. Like you're getting 50% each only. And then we take the ones after we again filter for spin plus half in the y direction and try to measure spin in the z direction. And we're still getting 50% of spin plus half in the z and spin minus half in the z. So if I just showed you these three experiments, you might tell me, why the hell did you do this? This is a waste of time. This is what anybody would expect. But let us see the fourth and final thought experiment. That is something which will not happen classically. So we measure spin in the z direction. 50% of them end up with spin half, 50% end up with spin minus half. We block the spin plus half and we let the spin minus half go. We measure the spin in the y-axis, and 50% end up with spin plus half, 50% end up with spin minus half. Cool. Now we block the particles with spin minus half, and we only take the particles with spin plus half in the y-axis, and we measure spin in the z-axis again. And interestingly, even though we filtered for spin minus half in the z direction earlier, now when we make this measurement, we get 50% with spin plus half and 50% with spin minus half. Yes, this is not a mistake or a joke. We filtered initially for spin minus half. Then all we did was measure the spin in the y-axis, and we took only the spin plus half in the y-axis. And now if we measure spin in the z-axis again, we suddenly have particles that have spin plus half in the z-axis, even though we filtered them out earlier. All we did was we measured spin in the y-axis in between. So yeah, a measurement of spin in the y in between suddenly managed to get us our spin in the z-axis with plus half again. If you think of this classically, that makes no sense. Like if you think of a classical vector, 3D vector, yeah, first issue is you can think of it will not have just spin plus half minus half. If you think of a general 3D vector, it can have components anywhere from 0 to half. And the second one is the third thought experiment. Like we measured the spin in the y direction, and that should not affect, like finding the component in the y direction should not affect what the component in the z direction originally was. That should not affect classically. So Like I said earlier, spin is a quantum system, and now using what we've learned so far, we will actually describe this quantum mechanically, and we will show how these measurements actually make sense, be it counterintuitively. So first, let's define a Hilbert space. So our Hilbert space is going to be a space of all 2D column vectors. Probably why I kept giving that example. Only difference is we are going to use it over the field of complex numbers. Okay. So if I take a general 2D vector, it will be two numbers, z1, z2. That is one vector. So let the basis vectors be the vectors with spin, be the states with spin minus half and plus half in the z direction. I'm going to use a notation which might seem very stupid, but it is the notation we use in quantum computing. And I don't want to use two notations for this, one today and one in the next session. So that's why I'm using this quantum computing notation now. I'll show you what the quantum computing notation is. So yeah, so the dual space is the space of all 2D row vectors, again over field of complex numbers, and we'll define the basis for both, and we'll also define the complex inner product. So if we look at the math, so yeah, SZ plus half, that state I'm going to define as 1, 0, like a typical I cap equivalent. Because we're working with complex numbers now, I'll not call it I cap, I just call it 1, 0. And I'm going to define the state as 0, the 0 ket. Why would I call it 0 ket? Because we're going to work with qubits tomorrow, and qubits are based of 0 and 1. So that's why. But the 0 is nothing but the 1, 0 column vector. And the spin minus half in the z direction, that state we're going to define as 0, 1 instead of 1, 0. And I'm going to call the state 1. So we have two basis vectors, 0 and 1. And these are the two states where with definite spin in the z-axis. So if we make a measurement in the spin in the z-axis, we will get either one of these two states. We either get 0 or we'll get 1. So our corresponding dual vectors will be the same row vectors, and we use the bra notation now. So just give me 1 second. Yeah, so this is our dual vector 1, and this is our dual vector 2. It's just the row vectors with 1, 0 and 0, 1. And so the complex inner product is the same as dot product, except when you take the dual vector, you have to take the complex conjugate. So suppose V is I times 0, that is our like V ket vector. We want to take the dual vector, it will become minus. So if I write V like this, it will become minus I times 0 vector. Or if I write it in terms of the row vector, it will just be 0, comma, oh sorry. It will just become minus I, comma, 0. Okay. Why would we take the complex conjugate? If you've seen complex linear algebra before, you know. If not, the motivation I'll give you is think of when we take the norm of a complex number. We take z bar to give mod z squared. So similarly, when we take the norm of a vector, we want it to be a real number, a magnitude. So that's why we take the complex conjugate. If you think of inner product of V with V, and V has complex numbers as its components, if we want a real magnitude, we need to take the conjugate and multiply it. So that is the motivation for why we take complex conjugate. You don't understand that? Just take it for granted. When we take a dual vector here, the components just become complex conjugate. Otherwise, it's the same. So now we have V is equal to I times 0. Just an example for dot product, and say W is equal to 0 plus 1 by root 2. And we take inner product of V with W. That will be minus I times 0 into 0 plus 1 by root 2. So this is nothing but minus I times inner product of 0 with 0 is 1. Like any states, when you take inner product with this, themselves, all the states are going to have single magnitude. So you get minus I by root 2. Yeah, probability amplitudes can be complex as well. If we, for example, I wanted to find the magnitude of this, I will take mod whole squared and it will just be half. Okay, so this is just an example to show you how our space is going to work for spin. So column vectors, 2D column vectors over the field of complex numbers. The corresponding dual vectors are row vectors. The basis is our usual basis. Just I'm going to use the notation for 0 and 1. And the only major difference is when you take a dual vector, you have to take complex conjugate of the components. And when you do inner product, correspondingly, you have to take the complex conjugate. Otherwise, what we've normally worked with, our two basis vectors are the states with spin in the z-axis plus half and minus half. Okay. Okay, so now let's try to explain the thought experiments one by one. So let's go to the first thought experiment. This is our first thought experiment. We start with some random vector. So sorry, random set of particles. So all the particles that come on the top have spin plus half. So they're all state 0 vectors, and all of the particles with spin minus half are all state 1 vectors. So when you measure spin in the z-axis for state 0 vectors, naturally all 100% of them are going to continue to remain in the state 0 since they're already in that state. Okay, so this is this thought experiment. And then we move on to the second thought experiment, where we first measure the spin in the x-axis and then we measure spin in the z-axis. So for that, what we need to do is we need to first define states with spin in the x-axis plus half and minus half. So what do we know? So we want to define two new states. We want to define, let's call them x plus and x minus. So these are two states with spin plus half in the x-axis and spin minus half in the x-axis. So what do we know? These are going to be two orthogonal states or perpendicular states. If the state has spin plus half in the x-axis, it does not have spin minus half. So that's why I've written inner product of state x plus with x minus is 0. So then we also know that inner product of states x plus or x minus with 0 or 1, that is, if we take a particle with spin plus half or minus half in the x-axis and then measure the spin in the z-axis, they are both equally likely to end up at half. So we know that probability is half. So I'm going to call the probability amplitude 1 by root 2. Yes, there could be some complex component, but since we are motivating and defining, I'm just going to call this 1 by root 2. So then, how do we know this? We just did the measurement. So our second thought experiment did this measurement. We got 50% x plus, and then we measured, and we saw that it has a 50% chance of going into the 0 state and a 50% chance of going into the 1 state. So that's why we got those probability amplitudes as 1 by root 2. So using this, we are going to define x plus and x minus. Again, I'm going back to our graph motivation. So suppose our z-axis spins had been like I cap and j cap, the way we define 0 and 1. If we wanted two perpendicular vectors with equal components, equal amplitudes on either side, we would go with I cap plus j cap by root 2. And we'd go with I cap minus j cap by root 2. Two perpendicular vectors with equal amplitudes on I and j. Yeah, there should be a plus minus half here. Typo. But yeah, amplitude with probability half. So using that inspiration, I'm going to define the x plus state as 0 plus 1 by root 2 and the x minus state as 0 minus 1 by root 2. So just like the graph suggests, since if our original basis was like the x and y axis, I'm just taking the two vectors at 45 degrees angle, two new perpendicular vectors. We could as well use this as a basis. So this is our x plus and x minus. And yeah, we can see that if we try to measure, now we can actually do this. So suppose I take inner product of 0 with x plus. That is, I have an x plus state and I'm going to measure 0. You can see that we will get a probability amplitude of 1 by root 2. And the probability is half. Right? Inner product of x plus with 0 is just inner product of 0 with 0, which is 1. Inner product of 1 with 0 is 0. So we just have 1 by root 2. So now you can see that why the x plus and x minus states have equal probability of ending up in the z-axis. So you've defined them well. You can take any measurement, x plus with 0, x plus with 1, x minus with 0, x minus with 1. You get the same probability of half. So now we go to our third thought experiment. So our third thought experiment, we had 3 different axes, sx, xy, and sz. And every time we made a measurement in one axis, we saw that there was a 50% chance of ending up with either spin in another axis. So now we need to define a third set of states that have spin half in the y-axis. So now I cannot give you a graphical motivation. We've already taken that. And this is where complex numbers come into power. This is why we need complex numbers. I can define my y plus as 0 plus I times 1 by root 2 and y minus as 0 minus I times 1 by root 2. Now you can check this for yourself. If with this definition, if I take inner product of y plus or y minus with x plus or x minus, we will get some. Let's do this example. In fact, let's take inner product of x plus with y minus. We defined x plus earlier, 0 plus 1 by root 2. So 0 plus 1 by root 2 into the newly defined y minus, which is 0 minus I times 1 by root 2. And what do we get? Inner product. So this inner product of 0 with 0 is 1 and 0 with 1 is 0. So if we take these two, we get a half into 1. And if we take the ones, we get minus I by 2. So half times 1 minus I. So now we want the probability. We just take square of the amplitude. So that is 1 by 4 times 1 minus I into 1 plus I. We can write amplitude of something like this as inner product of this conjugate times inner product of x plus with y minus. Basically, mod z squared is z bar z, and that's all I'm writing. Okay, so we get the probability to be half as we want. So this is telling us that okay, you made a measurement in the y-axis, you will end up in either y plus or y minus. If you take y plus or y minus states and you try to measure spin in x-axis or in the z-axis, then you have an equal probability of ending up in the plus half state or in the minus half state. So now we have 3 different bases. Like we have the 0, 1, which is the plus half minus half in the z-axis, and then we have the plus half minus half, x plus half and x minus half. Okay, there's a question. Can I answer it at the end? I will just finish the spin part in like 10 minutes and then answer the question. So yeah, before going into multiple spins, I will try to answer the question and then go. Okay, so just give me 10 minutes. Yeah, so where were we? So there is, yeah, we have defined different states. We've defined a normal 0, 1 basis, which is spin plus half minus half in the z-axis. And using them, we have defined our spin plus half minus half in the x-axis as well as the y-axis. And we've explained the first 3 thought experiments. So now, now we can use these. Now that we know, suppose we want to make a measurement in the z-axis for any general state psi, then what do? We just take inner product of 0 with psi and we take inner product of 1 with psi. This will give us the probability amplitudes, and with that we can find the probabilities. Same way, we want to measure sy for a random psi. We just take inner product of psi with y minus and we take inner product of psi with y plus and we take the magnitudes. So now we can make a measurement and find out the spin in the y direction. So we can now make any measurement, any of these 3 measurements on any general spin state psi. So we have built a system now. Now let's see if the system can explain that counterintuitive thought experiment 4. So let us go back to thought experiment 4 and see what happened. So initially we measured spin in the z-axis, putting the spin 0 plus half here and the 1 state here. So first we just selected all the 1 state. We're blocking the 0 state. Then we measured spin y and took the plus half, and then again we measured spin z. Okay, so now we have the 1 state to start with. Yeah, we are starting with the 1 state. Then we measure sy and take the positive spin. So what do we do when we want to measure sy? We find out 2 in, and we're going to take the positive spin. So let's take the inner product with y plus. So the inner product of 1 with y plus, that is the probability amplitude we're interested in. So y plus we defined as 0 plus I times 1 by root 2. Again, when we're taking the dual vector, remember the complex conjugate, that's why the minus here. So 0 minus I times 1 by root 2, inner product with 1, we get minus I by root 2. And now we take the square of the amplitude and the probability is half. This is what we saw, that 50% of them end up with spin plus half in the y direction and 50% of them end up with spin minus half in the y direction. 50%, 50%. Now the important point in quantum mechanics, the new state of the system of all of these particles is y plus. It is no longer 1. Okay. So now all of our 50% of particles are in the y plus state. And now we are going to measure sz again. So if we do that now, if we want to measure sz, and we take inner product of y plus with 0, and we find that that is nothing but 1 by root 2, probability half, and we take inner product of y plus with 1, we can calculate this to be I by root 2. Again, we get probability half, and now we see why, even though we had selected for spin earlier in the z-axis, spin 1 earlier, the measurement in the y-axis took us to the state y plus. And once we are in y plus, it does not matter. The memory that we measured the z-axis before is completely gone. All the quantum system knows is that it's in the state y plus now. And with this y plus, once we make a measurement, there's both an equal chance of ending up in spin 0 or spin 1. And that is why the experiment is as such. So now if I go back to the thought experiment, we can see and explain why, even though we selected for 1 here, when we do the y measurement, we are changing the state. It is no longer in 1. It is ending up in y plus, and y plus has a 50% chance of being spin plus half and 50% chance of being spin minus half. So that is why a measurement in the y-axis changes the state, and that is why we can measure again in the z-axis, and now we have a different result. So now the spin property, we can make any measurement and we can explain any such thought experiment. So with that, we have sort of explained quantum spin half in a small way. If you tell any physics person, you know spin half, quantum spin based on this, they will probably hit you. But this is the introduction. This is the fundamental idea. With more math and a more generalization, we can build this up to multiple spin half particles, spin 1, spin 3 by 2, and all of that. But this is the idea behind quantum spin. Same way you build a Hilbert space, like vector space, you define dual space, inner products, you define your different different measurements, and then you do the calculations. In outside of spin, more general quantum systems also will follow the same ideas, but the math will look very different. So like we mentioned earlier, that Hilbert space will have functions. So now my psi vector could be something like sin x, a function over x equal to 0 to infinity. And it might be weird to call these vectors, but they follow all of the properties we defined above. That's why we gave the general definition. Because the way we will use functions is using the same intuition, using the same thought process. We'll still talk about orthogonal vectors. We'll still talk about an inner product, but things that don't look like vectors. So that's why the general definition. So suddenly you might think, what is the dual vector psi? It will just be the complex conjugate of sin x, in this case, just sin x. And then what is the inner product? So the inner product between psi and phi will be something like phi psi dx integral from 0 to infinity, psi star phi dx. So we'll define an integral like this. This is not relevant to our rest of us. I'm just giving you to say why we gave the general definitions and why and how powerful this general definitions can be. And if we want a basis for this, like sin x indicates, we can define sin kx and cos kx as a basis, an infinite basis for our functions. This is how these same principles of building up using linear algebra ideas works for all quantum systems. So yeah, I will stop for a few minutes and answer that question. And if you have any other questions, ask me. There is just one small thing to hint at next session that I will cover after this. So I will come back to the call. Yeah, what was the question? How did we define spins in Y? So Ritu, was that answered later, or should I still answer that? Okay, I'm not getting an answer. So I will just go back and touch upon it quickly. So yeah, in theory, you asked me how did I just randomly define spin y as this 0 plus I cap and 0 plus I times 1 by root 2 and 0 minus I times 1 by root 2. It is not an analytical derivation. So to say, you can do a complete analytical derivation from the thought experiments. That is, you can just run Stern-Gallasch thought experiments. You can say these inner products all have to have this value. So this has to be my y plus and my y minus vector. You can do that. It will take longer and it will involve a lot more calculations. So that's why I just gave you a few thought experiments and I motivated this, so to say. I agree that you can say, why can't it be some other vector? But you can actually prove that these are the only two perpendicular vectors, unit magnitude, that you will find for both x-axis and y-axis that will have all of the measurement properties that you find while running Stern-Gallasch experiments. So I hope that answers that. I see another arrow. Yeah. Sorry, not an arrow. I see a hand. Too much quantum mechanics here.
So in quantum mechanics, we define spin qualitatively, right? We don't assign a quantity to it, right? So it is either
no.
plus half or
Spin is quantitative. Spin is very quantitative in quantum mechanics. Yeah. We don't talk about it qualitatively at all.
then it's either plus half or minus half, right? So,
yeah. For spin half systems, there are also spin 1 systems, spin 3 by 2 systems. They can have spin plus 1, 0, minus 1 and stuff. For our spin half systems, yeah, it's either plus half or minus half if we make a measurement.
so if you in the experiment that we did, like dividing it into Sx, Sz, etc.
Yeah.
And suppose there is a particle that has spin plus half, that will move similar to something that has maybe plus 1 by 4, or will it move different?
So no particle can have spin 1 by 4. That is physically not possible.
Can you take another example, like maybe plus 1 and plus half?
Okay, so a spin 1 particle, if we put it through the same Stern-Gallasch z-axis, it will split into 3 beams. There will be a beam that has spin 1 particles that will go like much above. There'll be a beam with spin 0 that will just go straight through, and there'll be a beam with spin minus 1 that will go below the minus half particles. So let me probably just draw this. Yeah, so suppose I am putting, say, both spin half and spin 1 particles through this SZ. You will end up seeing 5 beams almost. So one on the top will be all the spin 1 particles. It is coming, so I'm going to put an A and a B here so that I can notate here. So this is all the A type particles with spin 1, which end up having plus 1 in the Z axis. Then you will have the plus half, which are the B type particles that end up with spin plus half. There is going to be the particles of spin 1 with a spin 0 in the Z direction. So these are states. So I'll put the arrows. This is what type of particle it is. Then you will have the spin minus half states of the B type particles, and there will also be the spin minus 1 states for the A type particles. So if you just put spin 1 particles, you will end up with these 3 beams. If you put just spin half particles, you'll end up with these two beams.
For the spin plus 1, it will be
Yeah.
33, 33.
Yes, one third, one third, one third. If you take a normal beam, like without any bias. Yeah, you're right.
Yeah, okay. So also another thing like spin and then angular momentum. Is it
Yeah.
the same way we defined in classical? Like, do they actually spin, or is it just something that we are assigning it to the particle
So
mass?
spin is an angular momentum. Like if you make measurements on angular momentum and stuff, you have to include spin. But
Okay.
it is not an electron spinning on its axis that is causing that angular momentum. You can't use moment of inertia and say I omega, that is what is causing the angular momentum. That is not the case. We just know that this particle has some inherent angular momentum. Like it's electron is not actually a ball. Like it's something more. There's no proper visualization for it. We just have the wave function, but we know for a fact that it has some angular momentum intrinsic to it. We don't know what exactly, like how to visualize that, or at least I have not, in my knowledge of quantum mechanics, seen a way to visualize it. But what I know for a fact, it's not an electron spinning around. For an electron spinning around in a particular direction, it should behave like a classical vector, which we see it doesn't. It behaves differently.
Yeah, and when we are assigning spin and
Mm.
angular momentum to it, are we treating it as a particle or wave or both?
A quantum state. We are treating it as a quantum state. So that
Okay.
quantum state is neither a wave nor a particle. It's something defined specially. We saw that sometimes this quantum state's behavior is like a wave. Sometimes this quantum state's behavior is like a particle. So we're defining this electron as a quantum state. And we assign,
Okay.
yeah, spin to it. We don't assign, it has
Yeah.
spin always. When you read
This is
quantum mechanics textbooks also, a lot of times they will analyze the movement of the electron separately, the spin separately. But it has both always.
Yeah, so it's kind of a property of a quantum spin and angular momentum are properties of a quantum state. Like,
Yeah,
if
yes. If this electron is moving, say this electron is in a hydrogen atom in the p orbital, it will also have angular momentum because of being in the p orbital. It will also have the spin. So when you try to find its total angular momentum, you need to take into account both. Now we are thinking of free electrons. So these free electrons don't have any angular momentum due to movement, so to say. So it's just the spin.
yeah, thanks.
Okay, great. So okay, we have 10 minutes. So any other questions on the topic, you can just post in the group later. I will answer them. So the last part is just a hint at what is going to come in the session tomorrow. We're just going to touch upon multiple spin systems. So this was one spin half system. So what if we have a system with two spin half particles? So then we have to do something called a tensor product. But for now, just forget about the formality of the math. Just consider that this is how you would explain it. Just take my word for it. So we are going to define a new basis. So this 0 and 0 means that my two spin-off particles, my first particle is in state 0 and my second particle is also in state 0. So I'm saying that you can define the state of the two spin-off particles together like this. So 0, 0 means first particle is in spin 0, second particle is in spin 0. 0, 1 means the first particle is in spin 0, second particle is in spin 1. Third one means the first particle is in spin 1, second particle is in spin 0. And the fourth one means the first particle is in spin 1, second particle is in spin 1. So I'm saying this is the basis for our whatever wave functions. We're going to describe the spin of both particles together. So for example, I can define, say, my first particle to be in a state 0. It has spin the 0 state. My second particle could be in the superposition state, 0 plus 1 by root 2. You will recognize this as x plus. It could be in the x plus state. So when I write psi 1, 2, I will multiply these two and I will write them as 0, 0 plus 0, 1 by root 2. So this is how I will write the combined state of both particles. And in general, we go from 2D column vectors to 4D column vectors now because we have 4 basis elements now. We looked at these 4 basis elements. So with these 4 basis elements, we now have a 4D column vector and we can write it like this: 1 by root 2, 1 by root 2, 0, 0, the same vector. Okay. Or we can just write it like this. If we are comfortable like this, we can say, okay, this is the state of my first electron, sorry, first particle, this is the state of my second particle. So particle 1, particle 2, we just write it like this. We understand the spins of both particles. But suppose we take these 4 things as the basis. We took 0, 0, 0, 1, 1, 0, and 1, 1 as the basis. Now just consider the state of the combined 2 particles, 0, 0 plus 1, 1 by root 2. So how will you write this as some phi 1, phi 2? Well, for want of time, I would have let you try, but I'm just going to tell you, you can't. Like the earlier state, you could write like the 0 into 0 plus 1 by root 2. This means the particle of this first particle is in state 0, second particle is in this state. Now this 0, 0 plus 1, 1 by root 2, this guy, you cannot write like this. You cannot write as some phi 1, phi 2. You can just try. Mathematically, there is no way to write it like this. The only way you can write it is what is written here. You will say it is either in 0, 0 or in 1, 1. There is no way to split like this. And the reason is, it's very physical. The reason is, you cannot split it like this. It turns out is that the state of one particle depends on the state of the other particle. And this is called entanglement. So it means that these 2 particles don't have 2 separate states. Their states are actually dependent on each other. So this is called entanglement. So what happens? Suppose we measure the state of the first particle and we find it to be 0. So then what happens? That means we have found this phi to decompose into 0, 0 because it cannot be in 1, 1. So that means the second particle phi 1 is 0. That's what we found. That means phi has to be 0, 0. And that means phi 2 has to be 0. So by making a measurement on one particle, we are changing the state of the other particle. Similarly, if we made a measurement on the second particle and we found that phi 2 is 1, then we know that phi had to be 1, 1. So that means phi 1 is also 1. So that means a measurement of one particle changes the state of the other. I will just tell you this in classical language just to tell you how crazy this sounds. So we have 2 cats in 2 different rooms and 2 different car trunks. Both might be dead or alive. And if these 2 are entangled, what I'm saying is, if I open the trunk of one car and check if the cat is dead or alive, I automatically kill or make the other cat survive. I'm not kidding you. This is what happens in real life. This is actual quantum mechanics. This is entanglement. So if I open the trunk of the first cat, I see that it's alive. Then I know for a fact that the second trunk, if I open, the cat has to be alive. In fact, its state has changed. It is definitely alive now. So I can happily go open the second trunk and it will be alive. If I open the second trunk and I find the cat, so go back to square one, I open the second trunk, I find the second cat dead. It means automatically the first cat died at that moment. From the superposition state, it has gone into death. So not only does measurement change the state of the particle itself, if 2 particles are in an entangled state, it can change the state of another particle. And that is the hint at what we're going to do tomorrow. We're going to do multiple qubits and we're going to see a couple of algorithms that use these to do computations faster than any classical computer can. So that is a hint at entanglement and what we will see tomorrow. We will do this a lot more formally. We will introduce what is the tensor product. We'll introduce the space in which all these states exist, and we will see this in more detail. This I just wanted to get you guys excited for tomorrow. Okay, so can you still hear me?
Yeah, we can.
Yes.
Yeah. Okay, so has the presentation gone down or it's still there, right?
Yeah, it's still there. I can see your team screen.
Okay, cool. So any questions on this? I don't see any, so